So I hope you did a great job on the 1980 problem. Go ahead and check it here. You'll notice that in blue right here at the top of the screen, I was recording the given information. So when it said that the range would go from -1 to +2, I knew that the lowest y value would be at -1, which means the y value of your minimum point is at -1. So I didn't know at the time what to fill in for x. So I just left it blank. See here, so I had some x coordinate comma -1 would be the min. Similarly, if 2 is the highest value of the range, I knew the max point would have to have an a y coordinate of 2, even though I still didn't at that moment know the x coordinate. And then in red, I was also recording the given information. So when it said f of -1 equals -1, in other words, -1 is a point in the graph. So I knew I was going to do that, and you'll see on my graph in red, I plotted the 3 points that they gave me. Now, when it said -1, -1's a point in the graph, and I already knew that -1 was going to be the y coordinate of the min, I assumed that the only point that would have a y coordinate of -1 was that -1, -1, but I didn't fill it in because I didn't know if I would also find out that there was another min point with the same y coordinate. So that's why I left the blank there. So I started with the black chart, just like I did on the previous problem. Went through, was able to find the max. You're hopefully good with that in part A. In part B, you're asked to find the absolute min. And so I know to compare the left x and the right x of the domain to any critical value x's. But the only critical value that I got was a max, produced a max. I knew that from the second row here. Since the graph increases then decreases, I knew I was going to have a max at x equals 2. There was no need to compare the max to the left and right x values because I knew it couldn't be the absolute min. So if you already know the local maxes and mins, don't compare all critical values, just compare the local mins in order to find the absolute min. So since there were no local mins, then all I had to do was look at the left and right x values. So I hope this makes sense. Certainly, if there's anything that you're seeing that doesn't make sense, make a note of it so we can go over it in class together tomorrow. So here is a related problem, and I'm not just curve sketching, but I'm using these same sorts of ideas. So I have a position function, which is my f of x. And I'm going to analyze where the particle is moving forward and backward using the first derivative test. Well, it's been a while, but do you remember that the first derivative of position is? Tell me out loud. Say it loud. That's right. Velocity. I heard you. Good job. So the velocity is going to be, what? 6t squared minus 28t plus 22. And usually the best thing to do is factor these if you can, because we know that we tend to look for critical values from the derivative, and of course velocity is derivative. So I'm thinking I can factor out a 2 for sure, and I'll have 3t squared minus 14t plus 11. Let's see here. Will that factor further? The AC would be 33. And I could do 3 and 11. Yeah, that should work, shouldn't it? So if I have 3t squared, it has to be 3t and 1t. And I need 3 and 11. See if that works. And then let me double check and make sure my algebra is correct. So 3t squared minus 3t minus 11t is minus 14t plus 11. Awesome. So can you tell where the critical values are on this one? Can you see that I'm going to have critical values at t equals 11/3 and 1, because that's where the derivative v of t is equal to 0. V of t is never undefined, so I don't have to worry about picking up additional critical values. Now, if you're thinking, why is she doing this? I know that the particle is moving forward when the velocity is positive, and the particle is moving backward when the velocity is negative. So what I'm going to do is build a sign chart just like always. So I'm going to have 1 and 11/3. Let me make a little row for my test values. Y'all are certainly used to this at this point, I hope. I'm going to talk about V of t, and then I'm going to make inferences about S of t. So let's see here. I'm not even sure it wouldn't, well, yeah, I will. I was about to say I'm not sure it would make sense to go before 1, but of course it would because that's not 0. I do have positive time before that. So let's see. 11/3 is the same thing as what, 3 2/3? So I'll just pick 2 here and 10 here. So I'm going to plug into the velocity. When I plug in 0, I'm going to get negative negative, which is positive. When I plug in 2, I'm going to get what? Negative positive is negative. And when I plug in 10, I'm going to get positive positive is positive. So if the derivative is positive, I know the original function is increasing, the opposite for decreasing, and then back to increasing. So I can interpret from the t-chart that on the intervals from 0 to 1, I'm assuming 0, of course, and then 11/3 to infinity, the position function is increasing, which means the particle's moving in the forward direction. So the particle moves forward. On the time interval from 1 to 11/3, it moves backward. I'll just use it to save some writing here. So determine when the accelerating force is to the left and when the accelerating force is to the right. All that's saying is determine when acceleration is positive and when it's negative. So I'm going to change colors just a little bit. So I want the acceleration. Of course, that's just a of t. And if I go back to my original equation for v of t, that will be the easier one to take the derivative of. So I'm getting what, 12t minus 28. Well, that was easy. So if I want the hypercritical values, then I simply need to say that's going to occur at t equals 28 over 12 if the acceleration is equal to 0. It won't be a does not exist case. Divide by 4, that's going to be at 7/3. And I'm kind of assuming seconds, but the problem doesn't actually say, does it, what units of time we're using. So determine when the accelerating force is to the left and to the right. So I could make a quick second derivative t-chart with 7/3. And I'm just going to test 0 and 10 again. So I'll have a of t, and then I will make inferences about s of t, because a of t is your second derivative. So if I plug in 0, a of 0 would be negative. If I plug in 10, a of 10 will be positive. So I know that s of t is concave down and then concave up. So I can say acceleration is the force goes to the right, of course, on 7/3 to infinity. This is not the best way to write this. And to the left. On 0 to 7/3. It should technically be 0 to 7/3. So I could have chosen a test value like 1, for instance. So if I ask you to graph it, let's sketch S of t so that I'm not doing a brand new slide. Let's sketch S of t at the top. I've got a little more room there. So I've got 1 and 11/3 and 7/3 where stuff is going on. And you already know that this function has to be shaped something like this because you all know from pre-calculus and algebra 2 that that's a cubic function with a positive lead coefficient. So let's see here. I'm going to start with 0, 1/3, 2/3, 3/3, 4/3, 5/3, 6/3, 7/3, 8/3, 9/3, 10/3, 11/3, 12/3. So trying to not keep it too complicated to graph. Now, I know, and again, I'm not going to get real into y coordinates, but I know from my red graph here, my red sign chart, that I have a max at 1. So I might put that up here. And I have a min at 11/3. Now this is the first time you're going to see me do this. But what I'm going to do is I'm going to lightly say, okay, I know if the, well, you know what I can do too, and I'll go ahead and show you this. I want to find out where the particle starts. So notice I can use S of t and figure out that S of 0 is -5. So its initial position is down here. I know that the graph increases, then decreases, then increases. So I'm going to kind of lightly, if I had pencil, I would real lightly say it increases, then decreases, then increases. And I know it's not a pointy graph like that. It's not sharp. But that way I've got kind of the flow of where things are. Now, I know that I have a, notice right here, I have my point of inflection at 7/3. And so what I'm going to do is I'm just going to say wherever that blue line cross through 7/3, comma whatever, I'm going to mark that as the spot of my point of inflection. And now I'm going to go back and refine the graph and say, okay, from my dark blue point to my red point to my orange point, the graph is concave down. So now I make that decreasing and concave down come together. So I sort of refine the shape of the graph at this point. And then from my orange point to my red point and on forever, my graph is concave up. So now I refine the graph. So it's not just linear. It's actually a smooth curve. And that matches, remember, what I had in mind for the basic shape of the graph to begin with. And notice I never really graphed or did anything about roots like I would have done in Algebra 2 and Pre-Calculus. So let's talk a little bit more about points of inflection. I've talked a lot around them, but we've not actually done a lot with them. So we did this problem earlier, and remember I color-coded and said when the second derivative is negative, concave down, and when the second derivative is positive, you get concave up, and we see that. And I mentioned it then that since you see a change in concavity, whether it goes from concave down to up like it does here or vice versa, you get a point of inflection. So there's a point of inflection at x equals 0, and when I plug 0 in, I get 0. So 0, 0 is the point of inflection. So the points of inflection are easy to identify if you're already doing the second derivative sign charts. So let's do everything we know now, starting from the very top. How are you going to graph this cubic function? And keep in mind, you already basically know what it looks like. This will be a whole lot like the position function velocity acceleration problem we just did. So step 1, find f prime of x. It gives me 3x squared minus 12. Okay? Step 2, find your critical values. So that means, will f prime of x ever fail to exist? No. But f prime of x will equal 0. And you know, I've said this before, and let me go back. If you can factor f prime of x, go ahead and do it, because it's going to make so much of your work faster anyway to have that done and out of the way. So my critical values are only going to be at x equals 2 and negative 2. So those are the only candidates I've got for being maxes and mins. So what I do with that now is the f prime sign chart. So let me go ahead and set up negative 2 and 2 on my first derivative sign chart. Of course, I'm going to put my test values on row 1. I'm going to give you what happens when I plug into f prime of x on row 2. And on row 3, I'm going to put my inferences about the graph of f of x. So I'll bring it all together. My test values are going to be negative 5, 0, and 10. When I plug into f prime of x, I'm going to have a positive times a negative times a negative. Two negatives make a positive. So I've got increasing. I'm going to have a positive, positive, negative. And I'll have positive, positive, positive. Now, from there, I know where the graph is increasing and decreasing. If you've shown it on your green sign chart, you don't have to write that separately, not for me. You'll be asked to do so on the AP exam, but not for me. But you will want to start making your inferences. And your inferences from your green sign chart are that there is a max at x equals negative 2 and a min at x equals positive 2. Now, a lot of times I won't ask you to find the y coordinates by hand if it's really super messy, but I don't think this will be too bad. Let me do some scratch work here. I'm going to find the actual point that's a max. So negative 2, I'm going to do scratch work and then erase it. I go back and plug in to remember the original function. So negative 2 cubed is negative 8. Negative 2 times 12 is 24. And 24 then minus 5. So that's going to be 24 minus 13. And that's giving me, of course, 11. And then when I do f of positive 2, 2 cubed is 8. 8 minus 24 minus 5. So 8 minus 24 is negative 16. And negative 16 minus 5 is negative 21. I'm going to scooch my scratch work out of the way since I've still got quite a bit of things that I need to do. So let me just get that out of the way. So now, the next thing we need to do is proceed from all my first derivative information to the second derivative. So you know, I know by now it's better to write with a pen. So my second derivative, and I'm going to use the first version of my first derivative, is simply what, 6x? And of course that's easy because I know the hypercritical values. If I'm sticking with my color coding here, the hypercritical values are going to occur at x equals 0. And that's a super easy kind of thing to do because you know that it's simply going to go from negative to positive, because if I test it, I'm showing what's happening to the signs of f double prime and making inferences about the graph of f of x. So I'm going to test negative 1 and positive 1. I wind up getting negative 6 and positive 6. So I know concave down, concave up. And I know you know basically what this function looks like already. Notice I've not asked you to find the roots like you would have done in pre-calculus. But what we're doing is we're going through the work that reinforces what you already know about the basic shape of the graph. So I know, and I'm not going to ask you to spell out that the graph is concave down on negative infinity to 0 and concave up on 0 to infinity. If you've got it shown and labeled on your deep purple sign chart, good enough for me. But let's do say that I know you've got a point of inflection at x equals 0 because I do see a changing concavity. And then this is easy enough to plug in because if I do f of 0, then I get -5 when I plug into the original black equation. So now if I want you to graph it, you'll put it all together. So let me show you one last time how you kind of think through this. So let's see here. It looks like my big stuff's going on at -2, +2, and 0. So I'm going to spread those out a little bit. And I'm going to say we've got a max at -211. And I'm going to label max up there. You don't have to, but when I label stuff like that, it helps me not like somehow or another make a goofy error. It kind of keeps me on my toes. And then 2, -21. Okay, I'm going to tell you I'm not going to scale all that. I'm going to go right here. There's -21. So 2, -21 is your min. And then I know I've got a point of inflection at 0, -5. And I'll just write inflection right there, INF. Now, if it were a much more complicated graph, you wouldn't have any trouble at all doing what I'm fixing to do either. But remember, I'm going to kind of ghost in and say what I know is that the graph increases all the way to -2. X equals -2. So that means your graph's kind of has to go up to -2. And then from -2 to +2, it decreases, which makes perfect sense. And notice, while it's decreasing, it's got to pass through that point of inflection. And then from 2 onward, it increases. Now, clearly, once again, we know that graphs aren't so linear, and you're not going to have these weird corners where there's points of where they're not differentiable. But now I start to flesh out the graph, and then I say, okay, well, what else do I actually know about the graph? That's when you go back and say, all right, 0 and to the left, the graph is concave down. So from x equals 0 to the left, I'm going to make it concave down by making it go up and touch that max and then come down, and the shape of my graph becomes more refined. And then from 0 onward, concave up. So while I'm not exactly sure where the roots are, I still have a great looking graph using a whole different set of mathematical skills. Now let me show you one additional idea, and we will be practicing a little bit more. There is another idea called the second derivative test. So I know if I take a critical value from f prime of x and I plug it into the second derivative, that I can quickly tell if I've got a max or a min. Now, if you're curve sketching, this isn't as useful perhaps, but when we're doing optimization problems, which comes next in this chapter, this is a handy little tool. So notice that if you plug in a critical x value, and that's from setting f prime of x equal to 0 or figuring out where f prime of x does not exist. If you plug it into the second derivative and it's positive, then what you know is that the graph must be concave up at that particular x value. So if the critical value is either a max or a min, and the graph is concave up, then you know that the graph has got to be concave up, and the point that I was wondering whether it was a max or a min must be a min. And the reverse is true. If you plug your critical value, and remember, critical values are the candidates for maxes or mins. If you plug it into the second derivative and it turns out negative, a negative second derivative means your graph is concave down at that point. So again, if that critical value is a max or a min and you're trying to figure out which, It's got to be at the top of that little concave down place, so it's got to be max. Now, what we're going to do is we're going to test the new idea. Now, you've already done this problem once, so you may not have realized it, but I'm fixing to show you the exact same thing again. So I'm going to go through f prime of x like I don't already know this stuff, and I've got 3x squared minus 12. I've already said that's 3 times x squared minus 4, x plus 2x minus 2. I already have discovered earlier that my critical values were at x equals plus or minus 2. Now I'm pretending like I've not already done the sign chart and know which is a max, which is a min. The idea is if I now go into f double prime of x, and of course I know that f double prime of x is 6x. Here's how I use the information. F double prime of positive 2 is equal to 12. 12 is positive. Since the second derivative is positive, I know that f of x must be concave up at x equals 2. So this point right here must be where x equals 2 is. Therefore, I know that I've got a min at x equals 2. And then I'm going to say f double prime of negative 2 equals negative 12. Of course, negative 12 is negative. I know that f of x then is concave down at x equals negative 2. So if the graph is concave down, then the negative 2 must sit at the top. So now I've discovered that there's a max at x equals negative 2. If we go back and we look at this problem, notice I said max at negative 2, min at positive 2. In green there, max at negative 2, min at positive 2, and dark blue. So the two things agree. And while you won't use the second derivative test all the time, if all you're asked to do is find the maximum of something or the minimum of something and you're not actually curve sketching, this is a great shortcut. The other thing is, if you are asked to find maxes or mins, and it's extremely difficult to plug into the first derivative in order to do a sign chart, you'll sometimes find it's a lot less painful to plug into the second derivative. Of course, sometimes finding the second derivative is so entirely difficult that's hard. It would be harder to do this new test. So it's always sort of something you've got to think about. Now, what I'd like you to do is read this information, and I want you to go to the board, check this one out, and then we'll see how you did. Can you do this one at the board? So go ahead to the board while you still see this. Write k prime of x equals 4x cubed minus 12x squared on the board, and let's see if you can answer all the questions, and then we'll check. Take 5 minutes at the board.